Juan's problem was you put $300 a month into your bank. And the way interest works, right, is you get a certain percentage per year, but sometimes you get it monthly, right? You might get it twice a year, you might get it monthly, you might get it daily. Then there's what's called continuous interest, as if you're a limit, as if you're getting it interest on your money continuously all the time. But the easiest way to think of it is if your interest rate is 6%, which right now would be a miracle out there, because you can't get that kind of interest, then what would you get per month? Then the interest rate, but if it's monthly, you get that interest rate 6% divided by 12, which is, 0.5%, or 0.005, right? Make sense? So, if I started investing my money, let's beginning of month 1, end of month 1, beginning month 2, end month 2, beginning month 3, end of month 3. How much do I have at the very beginning, day 1 of the first month? 300, because I throw the money in the bank, right? Now, how much do I have at the end of that month?
301.50.
Yeah, 300, and he says $1.50 is the amount of interest you get, What's that, a half a pack of cigarettes nowadays? Is it less? If that. It's been a long time since I bought a pack of cigarettes. But it's 300 plus 300 times that I, right? I don't want to keep track of writing the number out there, so I'm just going to let that I equal that 0.5% or the 0.005. And if you multiply 0.005 times 300, he says you get $1.50, which makes sense. If you got 1%, it would be $3, right? So a half of 1% would be $1.50. Okay, so what do you have at the beginning of month 2?
300 plus 300 plus 300.
You throw in another 300, right? So you have another 300 plus what you already had. 300 plus the 300I. What do you have at the end of month 2? You have all of that times I, right? Because this is what you have at the beginning, now you get your interest. 300 plus 300 plus 300I, all times I. Okay, I'm hoping by now we can see a pattern. So let's see what is this if I was to multiply that all out. What do I have? Oops, that's not what I had, is it? What did I do wrong?
You forgot the 300. You got to put in the 300.
No, the beginning of the month we threw in the additional 300, right?
Like the next month is like
You add 300.
principal.
Beginning of month 2.
This is what I had at the beginning of the month, right?
Right.
What does this number represent?
Interest.
The interest.
Just the interest. I threw away the principal, right?
300 plus.
Oops.
That's what I was.
I have all of this. Plus all of this times I. Right? Month 1, you have $300 in the bank. At the end of that month, you have the 300 you started with plus the interest. Beginning of month 2, you throw another 300 in, you still have what you had last month. End of the month, you have what you had at the beginning of the month plus the interest on what you had at the beginning of the month. Right? Really simple. Okay. Let's multiply it all out. What do I have here? I have 300 plus 300 plus 300I plus 300I plus 300. What's going on here? Something's fishy. I don't believe my formula anymore.
Why do you have 300 plus 300i, the second term, in the,
At the end of month
two?
one, was it just?
Oh, we left an eye out, didn't we? Look, we're screwing up here. You gotta pay more attention. Don't try to, with 300, this much, right? Beginning of the month, we start with $300, we put it in the bank.
Wouldn't it be 300i?
Yeah,
Yeah, it should be just 300 die.
It's like an extra 300.
Well, because the 300 is the
The I was just the interest.
Oh.
And now I see what I've done wrong that's going to make this the hard way to do it. We could get there this way, but I'm going to start over. I'm going to start over because there's a lot simpler way to do it. What is this? This is the 300 times what? 1 plus I, right? That's the number I meant to make my I be.
Okay, yeah.
So to simplify things, this now is, we had 300 at the beginning. At the end of the first month, let's just write that number. We have 300 times 1 plus the interest, right? Which is 300. It was what we had was right. It's just a lousy way to write it. 300 times 1, that's your principal. 300 times I, that's your interest. What do we have at the beginning of the next month? 300 plus that, right?
Yeah.
Now, I may have lost some people with my lousy way of writing things. Are we caught back up? Start with 300. The end of the month, 300 times 1 plus the interest. 300 times 1 is the principal. 300 times I is the amount of interest you get. $1.50. Beginning of the next month, you throw in your additional 300, right? End of the next month, you take all of that. What do you multiply it by? One plus I, right? Because the end of the month, you have the principal. That's everything you started with times 1. Plus everything you started with times I to get the interest off of it. Okay, now let's multiply that out and see what we have. We have 300 times 1 plus I plus 300 times 1 plus I squared. Let's do one more, but then we'll definitely see the pattern. Let's just skip to end of month 3. The beginning of month 3, you have this much, right? So you're going to multiply that whole thing, 300 times 1 plus I, plus 300 times 1 plus I squared. You're going to multiply that whole thing times 1 plus I, right? You have all of that money times 1, that's your principal. You have all of that money times I, that's your interest.
Do you have the new 300 for month 3 added in
Oh,
there?
I forgot to throw the new 300 in.
Yeah.
Did we forget it last time too?
Yeah.
Man,
That's why we're here, Ted.
spring break.
Yeah. It's,
Must have already started. We started with 300. This is right, correct? Because we have 300 plus that at the end of the month. The next month we add the 300 in. Then we multiply all this, so that was okay. But the beginning of the month 3, yeah, I can't seem to skip, can I? So beginning of month 3, what do we have? We have 300 that we throw in plus
yeah.
that, right?
The stuff at the end of the month on the right.
End of month 2, 300 squared, wouldn't that be like 90,000?
No, 300, that's not squared, just the interest is part of squared, right? Mark, we've got 1 plus I times 300, and 300 times 1 plus I times 1 plus I. The 300 is not squared.
Okay.
Okay, so at the beginning of month 3, we have what we had at the end of the month plus the 300. So we have 300 times 1 plus I plus 300 times 1 plus I squared. Now I tried to skip and do the end of month all at once, and now end of month 3. What do we have? We have just this times 1 plus I, right?
Yes.
So I'll go ahead and multiply it all the way through. 300 times 1 plus I plus 300 times 1 plus I squared plus 300 times 1 plus I cubed. Okay, do we see a pattern between this one, and this one?
Yeah.
Can you tell me what we have at the end of 360 months, right? 3 years?
Yeah.
Yeah?
300, 3 years? 360.
So after 360 months, I sum from 1 to n of 300 times 1 plus I to the nth, right?
Yeah. All
'Cause
that to
isn't
the
that
35th, I guess?
The sum from I equals 1 to 3 of 300 times 1 plus I to the, oops, don't use an I, Ted, use a K. That what I had at the end of 3 months, right? I had a summation from 1 to 3 of 300 times 1 plus I, because I had 300 times 1 plus I to the first, plus 300 times 1 plus I to the second, plus 300 times 1 plus I cubed, right? So what do I have after 360? That's what I have, right? What can I do with the 300? Put it out front, right? Series, you can factor the 300 just like you could have factored it out each of those, right? That's 300 times the sum from K equals 1.
Yeah, what's the 360? Is that a year?
That's 12 months per year, 30 years.
Oh.
We're investing for 30 years?
Oh, I thought you said 3 years.
No. So we're investing. The question was,
Okay.
how much do I make? All right, how much do I end up with if I invest 300 per month at, it's 12% annually, it's 12% compounded interest, compounded monthly is what it is. It's 12%, no, 6%. 6% compounded is the fancy word they use, monthly, which is why we're doing this on a monthly basis, and then for 30 years. So the number of interest periods are the number of months. And each month I get that 6% divided by 12. That's my monthly interest. And so there's 360 total months that I'm interested in. Good?
Okay.
Calculus.
All right, so here we are. What kind of series is that? It's a geometric. That's what we've been studying, right? Things raised to the power. So what is that? That's 300 times 1 plus I. Well, now let's put in what I is. I was 6 over 12, which was 0.5%, which was 0.005. So that's 61 minus, remember our formula is 1 minus this to the nth plus first. So 1.005 to the 361 divided by 1 minus 1.005. Okay. Who's got a calculator?
I just lost.
Where'd the what come from?
369.
The 361 comes from the fact that the sum from, oops, I got to back up. I made a mistake. From I equals 0 to n of r to the k is 1 minus r to the n plus 1 over 1 minus r. But wait, I got to back up. I made a mistake. What mistake did I make?
You didn't add.
It starts at 0, right, is my formula. So what do I have to do here when I write this? Minus the 300 times the 0th term. But the 0th term is just 1.005 to the 0, so I just need to subtract $300 off from my answer there. I got that from my interest. The way to think of it is that the monthly interest is the annual interest is 6%. But you're getting your interest compounded monthly, which is the way it works in the real world, right? They don't give you wait till the very end of the year to give you your interest at the bank. They give it to you at the end of each month. So what monthly do you get? You get 6% divided by 12. Well, that's 0.5%. Well, a half is 0.5%, so that's 0.005. So the interest you get, if you take $300, the interest you get at that month is 1.005, because the amount that's still in your bank, you still have the $300 plus the interest. So the one keeps the $300, the 0.005 gives you your interest.
Oh, that's 1 times 0.05?
Yep.
1.
It's 1.005. You should be, the way to think of it though is like this, Scorpio. Think of it as 1 plus 0.005. Now, 300 times 1 is the $300 you have in the bank. They don't take that away, right? And then 300 times 0.005 is the amount of interest you get. So you add those two together, but it's easier to add them together first and put them in here.
Where did the top part of the expression come from?
Where
The top part of the expression?
it came from this formula. The formula for geometric series that we learned was that if you're adding up a finite number of terms, then it's 1 minus whatever the power, the thing that's getting raised to the power is, to the nth plus first, all divided by 1 minus that. Right? If it was a half, the sum from I equals 0 to 5 of 1/2 to the k would be 1 minus 1/2 to the 6th over 1 minus 1/2.
So we use that when it's not a fraction? Because if it's a fraction, don't we use a over 1 minus r?
The a is just the 300, right? I never write the formula down with an a, but if you want to, the formula for the a over 1 minus r is when this goes to infinity.
Okay.
Right? There's two formulas that you have to keep in mind. One for when it's finite, because this part only goes to 0 if the r is less than 1. Right? If we ask how much money will you have if we invest infinitely many months, you'll be infinitely rich. Right? So, but we got to use the formula for the finite. That's there's two geometric series formula. I only remember one of them. You can remember this one. This one goes to 0 as n goes to infinity. So then it's 1 over 1 minus r, which is the one you said. And I never put the a in there because to me the a is not a part of the series. I factor it out. Okay, anybody plug my numbers in?
6.05269 for the 105s.
I was hoping for a total number.
363,161.
And I think that's what Juan did for us on the backboard. If that's not exactly it, that's really close to what he had. And the interesting part of the problem, there's two interesting parts. One is, what if they were nice, gave you your interest up front? The whole formula changes just a tiny bit, right? Because you'd have 1 plus I here. So you'd have to just adjust a little bit. But if you work in financial mathematics, you have a bunch of formulas like this that they use. But if you want to do something new in financial mathematics, you get a degree in math, and you get a degree in business, and you go working in the financial industries, then it's the people that can go backwards from the formulas and change them to do something different that make the big bucks. So understanding where the formulas came from becomes very important if you're working out there in industry. I find the following to be the most interesting thing about this. The amount you put in, into the bank was what? 300 times 360, right? What's that number?
$108,000.
Even?
Yes, sir.
Really?
Yeah, really. You got $1.50 worth of interest at the end of that first month, and you think, this is not worth it, right? At the end of the first year, you put $300 a month in, and you got how much interest? Not very darn much, because it's not $1.50 times 12, right? Because you got interest on the interest each time. But even if it was $2 times 12, you got $24 worth of interest the first year. You're thinking, man, I put $300 a year, a month away for 12 months to get $25, $50 worth of interest. I mean, you can figure out this way exactly how much interest you get at the first year. You know how to do that. Just make this, right, a 12. Do the same problem with 12, find out exactly how much interest you get. But it isn't much. But the key is that the interest compounds. Every time you get interest, that first $1.50 of interest you got was in there for 30 years. The second $1.50 interest you got was in there for 30 years minus 1 month. The key there, and it's astounding, and people do not do this math, and so they do not realize that there's two things that are amazing. One is, this is 30 years, so if you start at 20 and you put $300 a month away and you get this kind of interest, it tells you the amount of money you can make. But what's reality is much, much greater than this, because when you get out of here, you'll have a retirement account wherever you get a job, and you'll be able to put a lot more than $300 a month away. But you can now figure out the question of, how much money do I need to put away? Now, summarizing this formula, what you figured out is P times the sum from I equals, or K equals, 1 to, what is it, number of years times 12, P equals amount, N equals number of years, I equals annual interest, times 1 plus I divided by 12. Equals the total amount. You use the exact same logic to reverse figure out if I need this much money, like you're borrowing this much money. Suppose this is the amount you're borrowing. You're going to buy a car, buy a $30,000 car. This is $30,000. You put in your interest rate. You divide through by this based on a 3-year or a 5-year or a 6-year note, and you figure out how much your payment will be, right? But then you can also figure out how much interest you're paying for that car. Well, if you haven't ever done the math on figuring out what the difference in interest in paying your car off in 3 years or paying it off in 6 years is, yeah, there's a huge difference. They love it. Why do you think car companies are happy to finance you out for 6 years on a car? Because they're making the price of the car an interest. I mean, these problems are well worth spending enough time on to master them to be able to figure them out yourself. Okay, any questions on these? You invested $100,000, you ended up with $350,000.
I do have a question.
Mm-hmm.
It's something I missed in the very beginning. It's how do you go from 0.5% to 0.5 to 0.005?
Percent means divided by 100, right? Right. So 10%. If I want to tell, I tell you the taxes on your houses are going to be 10% next year, and you have a $150,000 house. What do you do to figure out that you do times 10%? But it's not times 10%. It's times 0.1, right? You take 1/10 of this. Right. 10% means 10 divided by 100, which is 1/10. So your interest is 6%. You divide it by 12 to figure out what the interest is per month. The interest per month is 0.5%. 1/2 is 0.5. But that's percent. Now you've got to divide it by, 100. I said 10. You divide it by 100, right? 0.5 over 100 is 0.005. Oh. That's the number you actually multiply by, right?
Okay.
If you put 50% in your calculator, you do 50 and then you hit percent, all it does is divide by 100 to tell you it's 0.5.
That's why when you pay an extra mortgage payment, they take off the one from the back end of it, because it, damn.
If you know your mortgage stuff, then you make sure that when you pay off your house, when you make sure that you get the kind of mortgage deal where if you apply any principal it applies, if you pay any extra, that it doesn't go towards the interest, it goes towards the principal. And you make sure you do that so that, and there, you can look online, there's all kinds of, it didn't used to be this way, but there's all kinds of financial places online that'll show you got a 30-year note on your house. And at the end of each tax year, you'll throw $500 in principal towards it, and $50 each month that you'll pay the whole house off in 15 years. There's some really simple ways to pay your stuff off a lot faster, but the long and short is it's called financial responsibility. But if you don't know how much of a difference it makes, if you don't do a little bit of math to figure it out, or look at a website that'll help you figure it out. I mean, all this stuff can be calculated. Everybody knows the formula nowadays. It's a table. Put in your note, you can just experiment with the numbers and see if I increase $50 per month, how fast will I pay off my note? But look, I invest all my own money. I have since 1980s, before y'all were all born. But I deal with financial investors all the time who don't understand the basics of interest. They don't understand even the basics. So when you're sitting there thinking, oh, I'll go to Merrill Lynch and I'll let them invest my money. Yeah, I've been to Merrill Lynch. I fired them. I mean, you'd be astounded how little financial advisors often know. Okay, let's go back to calculus. So let's think about a series like this. If there aren't any more questions here, I don't know if I answered everybody's questions or not. It's well worth spending your time. If there's a problem you're going to work on, that should be the one you should do. I actually should tell one more story. I had fun with this. When I first figured all this stuff out, I was in graduate school and I was buying my first car. And I was just trying to figure out what my note was how much of a car could I actually afford, right? So I was trying to figure out, can I afford a $12,000 car, a $15,000, $20,000? So I was actually trying to figure this out. And I did it this way. I just did the math and figured it out, figured out the formulas. And then I got pretty good at figuring out, well, if it's this much and this much interest. So I'd go into the car guys. We'd walk back and say, oh, we'll figure out what your note's going to be on that. And I said, well, what's the interest rate while we're walking back into the office? And they say, well, I see we're charging 8% right now. And I'd say, well, let me see, $15,000 at 8%. We're financing over 3 years. Take the natural log of the square root of the exponential function, add the trigonometric cosine to the hyperbolic sine. It's going to be about a $217, $220 note, right? They'd be like, wow! I had to mess with them. I just couldn't help it. I'd done all the math in my head beforehand. So I couldn't possibly have done it on the fly, but I sure had fun with some salespeople.
But you intimidated them pretty good.
Yeah. They didn't try to mess with me with the numbers when they laid down, the numbers. Okay, so if I want to graph this sequence, right? The sequence of the terms. The graph looks like this. Let's see, at 1, we're at 1/3. I'm going to make the graph not to scale. Object and mirror closer than they appear. 2, 1/6. 3. 3. 1/9. Do one more. 4, 1/12. Right, and then go on forever, getting closer and closer and closer to the x-axis. So, if I want to compare this, what's the natural function to compare it to? Well, 1 over 3x, right? What's the difference between this function and this series? Just the domain, right? The domain of this is all positive numbers. And the domain of this is this sequence is just the natural numbers. Well, the whole point of what's coming up, the integral test here, the whole point of that is the following. Thinking back to Riemann sums, back at the very end of Calculus 1, you did some approximating integrals by adding up rectangles, right? Okay, what's the area of the black rectangle there?
Which one?
2/3.
This black rectangle.
The upper Raymond sum?
No, just this black rectangle. 1/3, right? Width is 1, height is 1/3. What's the area of this rectangle? 1/6,
Oh.
right? It's at height 1/6. Because this point, right, is the point 2, 1/6. This point is the point 1, 1/3. This point is 3, 1/9. So this one's 1/9 and this one's 1/12, right? So what can you tell me about the relationship between and the integral from 1 to infinity of 1 over 3x dx? Which one's bigger?
The one on the left where you add them up?
One on the left's bigger because it's 1/3 plus 1/6 plus 1/9 plus 1/12, right? And that's bigger than the area under this curve, right? And it's always going to be bigger because it keeps...
Oh. I see where this is going.
So, if this is bigger than this, then if I knew that this, we know how to do improper integrals, right? If I computed what this was and it turned out to be infinity, what's it say about this guy? This guy diverges, right?
It's infinity as well.
Yeah, it's infinity as well. So if the integral from 1 to infinity of 1 over 3x diverges, i.e. is infinite, then the sum from n equals 1 to infinity of 1 over 3n diverges. Okay? That clear? That good? Okay, let me draw a different picture. Or convolute this picture. Tell me the area of the red rectangle.
1/6.
1/6.
1/6,
1/9.
1/9, 1/12,
1/15.
1/15. So what does that represent? Well, it's not this sum, is it? But it's this sum minus the first term, right? So the red there is the sum from n equals 2 to infinity of 1 over 3n, right? Now, how does that compare to the integral? How does that compare to the integral from 1 to infinity of 1 over 3n? 1 over 3x. And the only difference here that I look at is that 2, right? Because by shrinking my sums of these rectangles to underneath, all I really did was start my series at 2. So what happened here? How does it compare to the integral now?
It's less than.
It's less than it, right?
Yes.
So what can I conclude? That if the integral, if the integral from 1 to infinity of 1 over 3x dx converges, then what do I get to conclude? This one converges also, right? Because if this is less than infinity, then this is less than infinity. So now, if this converges, and I add the first term back on, does it change whether it converges or not? What's the total of the first term?
It's
How big is the first term?
1/3.
Yeah, 1/3. If this guy converges, and I change this back to a 1, it converges too, doesn't it? Right? If from 2 to infinity you add them up and you get a number, and then you add the first one, you're just adding a third back to it, so it still converges.
What's the difference between these two?
Yeah.
So can you distinguish like a difference between, because it seems like the same thing
Yeah, it
actually
does.
converges when you say it diverges over here, but the only difference is you're using a different term for n.
Yeah, so try to think of them separately for the moment. You were with me here, right? You believe that this integral really was less than this. And so, I mean, yeah.
Yeah,
And
you're
so, you believe this was bigger than the integral. So if the integral turns out to be infinity, then this is going to turn out to be infinity. But by just throwing away the first term, so what I can, so maybe a way to compare them is this. Let's get all the things going the same direction. The sum from n equals 2 to infinity of 1 over 3n, we decided, I mean, you agreed with this, right? You believed it. You're just astounded that it works both ways, right?
Yeah, I mean, my question is, when you add one in, what makes it converge? I mean, when you start off with a different n.
Yeah, so let's put them all together. Let's put them all together, and I think maybe that'll help. This one, and then we got this one was less than. That's what we ended up showing, right? If we glued our 3 inequalities together. That n equals 2 to infinity of the series is less than the integral, and the integral is less than the sum from 1 to infinity. Right? So the integral is trapped between these two. So now, if this is infinity, what does that tell me about this one? What does less than infinity mean? Well, it doesn't mean anything, right? I mean, let's go back to two statements we made before. If this one's infinity and this one's bigger, it's got to be infinite, right? So if this one's infinite, if B is infinite, then definitely C is infinite.
But not necessarily
Right.
Huh.
2.
On the other hand, if this is infinite,
It's hard to understand.
and you subtract 1 away from it, isn't it still infinite?
Yeah, right? Should be.
So that one's still infinite too, right?
Oh, okay.
My question is is it like that because you're like taking a piece of it out, it's still going, both of them still going to infinity, but on one of them you're just taking a piece out.
That's right. They're going to both end up going to the same place. I mean, well, not exactly the same place, but if you have a series, let's call it. Let's not use an example here. Let's k equals 1 to infinity. It's a1 plus a2 plus a3 plus ... If this much of it turns out to be infinite, and you add 1 to it, you add the first term back in, it's still infinite, right? If this much turns out to be finite, and you add the first term back, it's still finite, right? So adding or subtracting that term doesn't affect whether that series converges. What's important here is that we manage to squeeze this in between these two, so if B is less than infinity, then it's finite, then this one's also got to be finite, right?
Okay.
So if this one's finite, then A is finite. So this guarantees me, what does it end up telling me? It says if this integral converges, then this series converges, right? And if this integral diverges, this series diverges.
Got a question. Okay, you say if B is less than infinite, then A is finite. So would it then be true that A is still finite if you add C to it?
If you add the one more term to turn it into C,
Okay.
it's still finite.
Okay.
Right, that's what I'm saying down here. If you have a sum, and it goes from 1 to infinity, and you figure out that this much of it is finite, and you add that one back in, it's definitely still got to be finite, right? Okay. In our case, we're adding a whopping 1/3 to it. So if it's finite from 2 on, then it's finite. So this is the bigger theorem known as, we did an example, but this is the bigger theorem known as the integral test for series. Because if you have a series and you look at it and you go, hey, if I turn this into a function and I can integrate it from 1 to infinity, then if that integral exists, then that series is finite. And if that integral doesn't exist, if it diverges, then that series doesn't converge. So your next few problems in the notes are exactly this kind of thing, asking you to do something like this, like with 1 over x squared, and asking you to figure out this concept that I've tried to illustrate here, where, the sum from k equals 2 to infinity of ak is equal to the sum from k equals 1 to infinity of ak plus, minus a1, right? And you can changing it from 1 to, so which is why this series converges if and only if this one does, because they only differ by that first term.
Is your k supposed to be 1 and your k supposed to be 2 in it? Are they supposed to be switched? That doesn't seem like.
If I go from 1 to infinity and then I subtract off the first term,
okay.
How many terms do I have left? 2 to infinity. Yeah, I had trouble writing it too, but you got it. Other questions there? Well, then let's finish it up and figure out for once and for all whether this series converges, right? Because we need to compute this integral. And we all know how to do that because I think that one was on your test. But we'll remind you. How do I integrate that? What do I do? If I want all my points, if I don't want Brandy to dock me, first thing I have to do is...
Put equal sign.
What?
Put equal sign.
Yeah, you better have your equal signs, that's for sure. Limit, right. Limit as what? Something goes to infinity of integral from 1 to n, right? That's the whole point. We can't integrate from 1 to infinity, but we can integrate from 1 to n and then take the limit. Now, can you integrate it? I know it's spring break, but can we still integrate? And the derivative of that would be 1 over 3x times the derivative of the inside, which would be 3. I better put a 1/3 out front, right? Right, derivative of that would be 1 over 3x times the derivative of the inside, but I've got it times a third, so the 3's cancel, I end up with a 1 over 3x. What's that equal to? Oh, wait, from 1 to n? So that's the limit as n goes to infinity of 1/3 natural log of 3n minus 1/3 natural log of 3, which equals
8.
what's it equal? Infinity, right? Natural log grows forever. So that's infinity. So now, what do we know about this series? Right. It's bigger than this. This is equal to infinity, so this doesn't exist, right? Now, there's something very important to notice here. What's the limit as n goes to infinity of 1 over 3n? What's the limit of the terms?
It gets smaller and smaller to 0.
Right, it's 0, right? Now, before, remember when we added up a half, I said I'd take a half a step to the door, then I take a quarter step to the door. We added up forevermore, right? I never got to the door.
Right.
It ended up being I took a total distance of 1 step, right? A half plus a fourth, that's 3/4. Plus an eighth, that's 7/8. Plus a 16th, that's 15/16. 31 32nds, 63 64s. 123 124s?
Yeah.
No,
28.
127 128s. Anyway, I never make it to the door. But here, if you take a third of a step each time, go a third of the distance each time, you go past the door. That's really surprising, but 1/3 plus 1/9 plus, I'm sorry, 1/6 plus 1/9 plus 1/12 plus 1/15 plus dot, dot, dot. The terms are getting smaller and smaller and smaller, but it's still, I can see Kyron, he's worried back there. He's like, uh-oh, this doesn't make sense anymore. The terms are getting, so right? The terms are getting smaller and smaller and smaller. It ought to add up to something, right? Yeah, but it doesn't, because we know for a fact that the area under this curve is infinite. And we know that this series adds up to more than the area under that curve. So it was a shocking fact to mathematicians to discover. You think if the terms are going to 0, if the terms are getting smaller and smaller, the series ought to add up to something. No, it doesn't. There's no guarantee of that. So that's a surprise. Now, if the terms don't go to 0, then it definitely adds up to something, right? Because if the terms don't go to 0, you're adding 1 plus 1 plus 1 plus 1 plus 1, or a half plus a half plus a half plus a half. If they don't get down to 0, you've got to end up to be infinity. But just because they do tend to 0 doesn't mean that it doesn't add up to infinity.
So these are like special cases, per se?
Well, they're not as special as you'd think. It's that there are tons and tons of series where the terms go to 0 and they don't add up. And the next few weeks we'll be discovering different tests to try to figure out which series add up to be something and which ones don't. Because series are what you use in electrical engineering for voltages, AC and DC, and these series are a huge part of differential equations, electrical engineering, all that stuff. Stay off the street. I will see you after the break on Monday with some problems.